When sizing a feeder for a 480 volts 3-phase panel board, the feeder size is determined by the load on the panel board. The panel board rating represents the maximum allowable load that can be connected to the panel board, and it's the feeder's job to be able to handle the maximum potential load. To determine the appropriate feeder size, you need to calculate the total load connected to the panel board. This involves summing up the amperage of all the branch circuits connected to the panel board, taking into account any applicable demand factors. Demand factors allow for the fact that not all loads will be operating at their maximum capacity simultaneously. This is especially important in situations where there are numerous loads with intermittent operation, such as lighting, motors, or 8-track equipment. NEC Article 220 provides guidance on calculating branch circuit, feeder, and service loads. It covers various occupancy types and load types, offering specific demand factors that can be applied. For example, NEC Table 220.42 provides demand factors for general lighting loads in different occupancy types. NEC Table 220.53 offers demand factors for household cooking appliances. After applying the appropriate demand factors, you'll arrive at the calculated load for the panel board. This value represents the estimated maximum demand that the panel board will experience under normal operating conditions. It's important to note that the calculated load should not exceed the panel board's rating. The panel board rating is the maximum amount of current that the panel board is designed to safely handle. If the calculated load exceeds the panel board rating, you'll need to either reduce the load or upgrade the panel board to a higher rating. Typically, the feeder breaker and cable are sized at 125% of the panel board rating. This 125% sizing factor provides a safety margin to account for load diversity, potential overloads, and future load expansion. Sizing the feeder components at 125% ensures that they can safely handle the continuous load and any short-term overloads without overheating or failing. For example, if the panel board has a rating of 200 amps, the feeder breaker and cable would be sized for 250 amps, which is 200 amps multiplied by 1.25. This means the feeder breaker must be rated for at least 250 amps, and the feeder cable must have an ampacity of at least 250 amps. The ampacity of a cable is the maximum amount of current that it can safely carry without exceeding its temperature rating. The ampacity of a cable depends on several factors, including its size, insulation type, and installation method. NEC Table 310.16 provides ampacity ratings for various types of conductors under different installation conditions. When selecting a cable for the feeder, it's important to choose one with an ampacity that meets or exceeds the calculated load plus the 125% sizing factor. It's also crucial to consider the voltage drop in the feeder cable. Voltage drop occurs when the voltage at the end of the feeder is lower than the voltage at the source due to the resistance of the cable. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. NEC Section 215.2 provides guidance on voltage drop considerations for feeders. It recommends limiting the voltage drop to no more than 3% for the feeder and no more than 5% for the feeder and branch circuit combined. To minimize voltage drop, you can increase the size of the feeder cable or reduce the length of the feeder. In addition to sizing the feeder breaker and cable, it's also important to select appropriate overcurrent protection devices for the branch circuits connected to the panel board. Overcurrent protection devices, such as circuit breakers or fuses, are designed to protect the branch circuits from overloads and short circuits. The size of the overcurrent protection device should be matched to the ampacity of the branch circuit conductors. NEC Section 240.4 provides rules for protecting conductors against overcurrent. It specifies the maximum allowable overcurrent protection for different types of conductors based on their ampacity. When selecting overcurrent protection devices, it's also important to consider the interrupting rating of the device. The interrupting rating is the maximum amount of fault current that the device can safely interrupt without failing. The interrupting rating of the overcurrent protection device should be greater than the available fault current at the point of installation. Available fault current is the amount of current that would flow in the event of a short circuit. It depends on the impedance of the power source and the impedance of the circuit. A qualified electrician can calculate the available fault current using appropriate methods and equipment. The calculated fault current should be less than the interrupting rating of the circuit breaker or fuse. Grounding is another critical aspect of electrical safety. A grounding system provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection device and clear the fault. NEC Article 250 provides detailed requirements for grounding electrical systems. It covers topics such as grounding electrodes, grounding conductors, and equipment grounding. A grounding electrode is a conductive object that is buried in the earth and used to establish a connection to ground. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. A grounding conductor is a conductor that connects the equipment grounding system to the grounding electrode. The size of the grounding conductor is determined by the size of the series entrance conductors. Equipment grounding refers to the connection of non-current carrying metal parts of electrical equipment to the grounding system. This helps to ensure that any fault current will flow back to the source and trip the overcurrent protection device. Bonding is also an important part of the grounding system. Bonding is the connection of metal parts of electrical equipment to each other to create a low impedance path for fault current. This helps to reduce the risk of electric shock. NEC Section 250.92 provides requirements for bonding service equipment. It requires that all metal enclosures, raceways, and other metal parts of the service equipment be bonded together. Arc flash is a dangerous electrical hazard that can occur when a high-voltage arc is created between two conductors. Arc flash can cause severe burns, blindness, and even death. To protect workers from arc flash hazards, it's important to perform an arc flash hazard analysis. An arc flash hazard analysis is a study that determines the potential arc flash hazard levels at various locations in the electrical system. The analysis takes into account factors such as the available fault current, the clearing time of the overcurrent protection devices, and the working distance from the energized equipment. Based on the results of the arc flash hazard analysis, appropriate personal protective equipment, or PPE, can be selected. PPE includes items such as arc-rated clothing, gloves, and face shields. NEC Article 110.16 requires that electrical equipment be marked with the available fault current and the arc flash hazard information. This information helps workers to understand the potential hazards and take appropriate precautions. Coordination studies are performed to ensure that overcurrent protection devices operate in a coordinated manner. A coordination study helps to minimize the extent of an outage by ensuring that only the overcurrent protection device closest to the fault trips. Coordination studies also help to prevent nuisance tripping of overcurrent protection devices. A qualified electrical engineer can perform a coordination study using specialized software. The coordination study takes into account the characteristics of the overcurrent protection devices, the impedance of the circuit, and the available fault current. The results of the coordination study are used to adjust the settings of the overcurrent protection devices to achieve optimal coordination. Selective coordination is a type of coordination that ensures that only the overcurrent protection device closest to the fault trips, even under high fault current conditions. Selective coordination is often required in critical facilities such as hospitals and data centers. NEC Section 700.27 requires selective coordination of overcurrent protection devices in emergency systems. Power quality refers to the characteristics of the electrical power supply. Poor power quality can cause equipment to malfunction, operate inefficiently, or fail prematurely. Common power quality problems include voltage sags, voltage swells, harmonics, and transients. Voltage sags are a temporary decrease in voltage. Voltage swells are a temporary increase in voltage. Harmonics are distortions of the sinusoidal waveform of the electrical power supply. Transients are short-duration, high-voltage spikes. Power quality problems can be caused by a variety of factors, including nonlinear loads, switching events, and lightning strikes. Nonlinear loads are loads that draw current in a non-sinusoidal waveform. Examples of nonlinear loads include electronic ballasts, variable frequency drives, and computers. Switching events are events that cause a sudden change in the electrical circuit, such as starting or stopping a motor. Power quality problems can be mitigated by using power quality equipment, such as surge suppressors, harmonic filters, and voltage regulators. Surge suppressors protect equipment from voltage transients. Harmonic filters reduce the level of harmonics in the electrical system. Voltage regulators maintain a constant voltage level. Regular maintenance is essential for ensuring the safe and reliable operation of electrical equipment. Regular maintenance should include visual inspections, testing, and cleaning. Visual inspections can help to identify potential problems such as loose connections, damaged insulation, and corrosion. Testing can help to verify the proper operation of electrical equipment. Cleaning can help to remove dust and debris that can cause overheating or malfunction. Maintenance should be performed by qualified personnel who are familiar with the equipment and the applicable safety procedures. Lockout-tagout procedures are used to prevent accidental energization of electrical equipment during maintenance. Lockout-tagout procedures involve disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch. The lock and tag prevent the switch from being turned back on until the maintenance is complete and the lock and tag are removed by the authorized person. NEC Section 110.26 provides requirements for working space around electrical equipment. It requires that there be sufficient working space to allow for safe access and maintenance of the equipment. The amount of working space required depends on the voltage of the equipment and the location of the equipment. The working space must be clear of obstructions and must be adequately illuminated. Safe work practices are essential for preventing electrical accidents. Safe work practices include using appropriate personal protective equipment, following lockout-tagout procedures, and maintaining a safe working distance from energized equipment. Workers should be trained in safe work practices and should be aware of the potential hazards of working with electricity. When working on or near energized electrical equipment, it's important to use insulated tools and equipment. Insulated tools and equipment are designed to protect workers from electric shock. The insulation on the tools and equipment should be in good condition and should be rated for the voltage of the equipment being worked on. Rubber gloves are an essential part of personal protective equipment for electrical workers. Rubber gloves provide insulation from electric shock. The rubber glove should be inspected before each use for any signs of damage, such as holes or tears. The rubber glove should be rated for the voltage of the equipment being worked on. Eye protection is also important when working with electricity. Eye protection can protect workers from arc flash, flying debris, and chemical splashes. Safety glasses or goggles should be worn whenever there is a risk of eye injury. Hearing protection should be worn when working in areas with high noise levels. High noise levels can damage hearing. Earplugs or earmuffs can be used to protect hearing. Fall protection should be used when working at heights. Fall protection can prevent serious injuries or death from falls. Fall protection equipment includes safety harnesses, lanyards, and lifelines. Confined space entry requires special precautions to ensure the safety of workers. A confined space is a space that is large enough for a worker to enter, but has limited means of entry and exit and is not designed for continuous occupancy. Confined spaces can contain hazardous atmospheres such as toxic gases or oxygen deficiency. Before entering a confined space, the atmosphere should be tested to ensure that it is safe to breathe. Workers should be trained in confined space entry procedures and should use appropriate personal protective equipment. Electrical safety is a critical aspect of electrical work. It is important to follow safe work practices and to use appropriate personal protective equipment to prevent electrical accidents. Electrical workers should be trained in electrical safety and should be aware of the potential hazards of working with electricity. By following these guidelines, you can help to ensure the safe and reliable operation of electrical systems.